Okay, thank you. Can everyone hear me? Professor Sawyer, can you hear me?
Yes, we can hear you.
Okay, all right, good. So I thought for a moment that I would have to give my presentation using sign language. So I think that would be a big challenge, but we all have to meet challenges. All right, so I'm going to talk today about machine learning and prediction of sequential images. So this follows along with work that uh, I did together with Eslam Hussein at the Department of Computer Science, University of Western Cape, and Dr. Mehrdad Ghaziaskar was also a supervisor in this work. I do want to try to be as interactive as possible, especially when you have a situation like this where there's a distance and it's hard to connect. I think people will fall asleep if you don't have some chance to interact. So what I would like to do is make sure that we are all connected. Please type in your university into the chat window so I can get some idea of, give me your university and department. And type that into your chat window so we can see that everyone is connected, and we can also see where that everyone knows how to use the chat. So if you don't know where the chat button is, I think it's on the lower left, I believe, lower right, I believe. So please take a moment, everyone, to type in your university and your department. So I got one from, okay, very good. So I'm getting some from University of Lagos Department of Computer Science, very good. So I'm getting some idea of what everyone is. Yes, Professor Olero, welcome. Okay, okay, yes, okay, math. Okay, there's someone from University of Lagos. Very good. Okay, so let's see. Okay, Dr. Psina, nice to see you, or see your name anyway. Okay, okay, yes, okay. This is fine. Okay, so someone from Ife. Very nice. Okay, I saw my student from Benin. I don't know if he's there. He hasn't responded. Okay, good. So from Port Harcourt. Very nice. Okay, so we've got many people from Lagos. I do want to reinforce what Dr. Sawyer said, that please do send your comments in the chat window or raise your hand, because I think it's very valuable to have questions. And people hesitate to give questions because they may think that the question is not smart, but I can tell you that if you have the question, I'm sure that someone else will benefit from your question. I say that the only stupid question is the one that's not asked. So please feel free, and everyone can learn from your question. This also helps me to know what level I should put this presentation at. I see some people from computer science. You may know already everything that I'm going to say today, but hopefully I can give a new perspective and we can have a discussion. So I'm hoping that we can all learn together. Okay, all right. So let me make sure you're all with me. Please type OK in the message window and I'll go on to the next slide, if that's okay. Is everybody there? Okay, so I got one. I need 5 OKs before I go on. 1, 2, 3. Okay, I've got 3, 4. One more. Okay, there we go. Very good. Okay, so let's go on. So, all right. So Dr. Sawyer already gave my introduction, so I won't say anything more. Just you can see at the lower left. I don't know if you can see my mouse, but if you don't know, I have spent
Can see your mouse.
many happy months in Nigeria. Most recently in Abuja at AUST, And I really wish I was there with you, and I miss you all very much. And by God's grace, I'll be able to come back and visit you. You may not have seen my family. I have 4 children. And just to say that none of them are in mathematics, but my daughter Esther is a data scientist. And she probably knows more about what I'm talking about today than I do. But unfortunately, she's not able to join me. So, all right, so let me give an outline of what I'm going to talk about. So I'm going to go back to foundations just to make sure that we have the same language and the same understanding. What is the basic purpose of machine learning? So I'll talk a little bit about that. And because I'm a mathematician, I may give a little bit more mathematical perspective on this issue. Then I'll talk about 3 tiers of machine learning methods. There's basically 3 levels, the classical, the modern, and deep learning. Okay. Now, from there, I'll pass on to making the right choices. There are many, many choices involved in using machine learning. And unfortunately, many people make wrong choices. And I hope that I can give you some ideas about how to avoid wrong choices. When I was making up this presentation, I was wondering whether I should say thou shalt nots or thou shalt. So I decided to make it more positive and say thou shalts. But there are some pitfalls that you need to avoid and some good practices that will help you from making mistakes. Unfortunately, there's a lot of published literature that is faulty because of some faulty methodology. Okay, and then I'll give a hands-on code demonstration, and probably in my next session, we'll do more hands-on. Now, I don't know, Dr. Sawyer, if you want to record this, that's fine. That might be a good idea. Certainly, I will
make it recorded.
Oh, it's being recorded? Okay, all right, very good. All right, so all of these points will be illustrated with reference to our particular research, which involved groundwater prediction based on monthly satellite data. Now, that's not a very clear description of what we did, but I will make it more and more clear what we actually are doing, did in our research. But it is basically, as the title says, sequential image prediction. You have a time-ordered sequence of images, and you want to predict the next image in the sequence. Okay. So this is a little different, say, from facial recognition, which is one of the, or a handwriting recognition, which are, or some other kind of classification, which are common applications of machine learning. Okay, all right. So here I'm going to say basic pillars of machine learning and make 4 points here. Let me, just a moment, I'm expecting my colleague Eslam to join, and he may have messaged me, so just give me a moment and see. All right, so let me go on with this. Okay, so the purpose of machine learning, I think that people may not think of it this way, but the purpose of machine learning is to create a function. Really, that's what machine learning does, is it creates a function. And it creates this function based on information from a data set. Now, the elements of the data set are data vectors. Now, more precisely, you would say it's not a set, it's not a vector, but an array. But you can think of vector or array as a set of numbers, and elements of the data set are arrays or vectors of numbers. Okay, machine learning functions associate useful properties with the data vectors. That's what the function does. A function associates a value or some kind of ID with objects. So this is the purpose of machine learning, is to associate useful properties with these data vectors. And machine learning functions can be applied to other data outside the original data set. That's why machine learning is so useful, because something that you derive from a limited set of data can be applied in general. Okay, and as I said, please interrupt me anytime you want to ask questions. Okay, and it's not going down. There we go. Okay. All right, now, so let me just draw a little bit what I mean by a function. All right, so there's a abstract representation of function. So I can think of a function as something that has a domain. And it has also has, mathematicians call it codomain. So here's my domain here. And here's my codomain here. Okay, and these are just representations of general sets. Okay, so the function is I can draw an arrow here, and what a function does is it assigns elements in the domain to elements in the codomain. So every element in the domain goes to something in the codomain. All right. Now I can say there are two types of functions. We can say discrete or continuous. Okay. So if I have a discrete function, then my codomain would consist of discrete points. Okay. So here's my codomain, it's discrete points. Okay. Then in my domain, every element in my domain will map to one of these discrete points. So for instance, this one might go here. This one might go to the same point. This one might go to the same point. Okay. So let me just call this 1, 2, 3, 4, 5, 6. Now, if I look in the domain and I find all points that map to 1, that gives me a subset of the domain. So all the points in this subset of the domain map to 1. Okay. Then I'm going to have a subset of the points in the domain that map to, these all map to 2. So all the points in this subset will map to 2. So this would be characterized as 2. Then I have 3, and then I would have 4, and then I would have 5, and then 6. So notice I have divided this domain up into regions. This is mathematically, this is called a partition. So I've used this discrete function creates a partition. Okay. All right. Now, what I've done here is I've actually classified the elements of the domain. So this classifies of the elements of the domain. Okay. Now, let me ask the organizers. My colleague would also like to come in, and I thought that we could reuse the same ID, and he is not able to reuse the ID. So I wonder if you can send me another ID. Let me ask him. I'll send you his email.
Can you give him the that you use so he will register and will allow him in? Just give us his name. Just tell us his name. So
okay. All right. His name. I'll give you his name here. Okay. Okay. Oh, sorry. That's not. I sent that privately, so I'll send that to here. His name is. Okay. All right. So here, let's try. I don't know.
He's already in. He's been allowed in.
He's been allowed in. Okay. All right.
Yeah.
Wonderful. Okay. Okay. All right, so he will assist me, especially if I say something wrong, or or especially when we do the code. I hope that he will be able to. I hope that he will be able to talk also. Okay. All right. Good. All right. All right. So this is for a discrete function. So discrete functions are used for classification. So just to emphasize that point. So okay, and classification can also include clustering. Right. Clustering means that your classes are not predefined, but the classes are defined by the data itself. Okay, so this is a discrete function, and most machine learning involves discrete functions. However, you also have something that you could call a continuous function. So let's look at continuous functions. Okay, so here we have a domain, and you have your codomain. And I'm going to make a continuous function. Okay. In this case, I don't have discrete values here, but I have something like a scale of values. Like here, I could go down from 0 on this end, and then maybe up to 1,000,000 up to this end. Okay, so I have a continuous scale. Okay, and let's say the scale goes like this. Okay, so 0, maybe this is 100 here. This is 1,000. This is 10,000. Okay, so say right here, this is between. Well, actually, I shouldn't do it this way. I should do it. I think a better representation. Let me redo this. I can just write this as a scale. I don't need to have a set like this. I just make a scale. Okay. All right. So I'll just go from 0 to say 1,000,000, and then I have these levels here. Okay, like I said, 100, 1,000, and then 10,000, and 10, something like that. Okay. Now, if I look at the points that map to say 100 here, if I look at those points in this domain, now they'll no longer form a region, but they'll form maybe something like a line. So the points that map to 100 may form a line. So 100. Then, and this may not be such a regular line. It may be very irregular. It may look something like this. Okay, so maybe 100 maps here. Maybe 1,000 maps here. Okay. So you could call these contour lines. Okay. Okay. So what I've done is I've created a kind of a, well, you could say this is like a topography. Okay. And if you represented this on the computer, this would be like an image plot. Okay. So I've created a topography on my domain. So this continuous function doesn't, now I could take any one of these contour lines and make a classification. I can make a classification to the left or to the right of this contour line. So that would be the ones below or above this threshold. That would be one possibility. But sometimes you do just want to get the continuous value. So continuous functions, the use of continuous functions are often for prediction. Okay, or kind of like a measurement. And in fact, practical measurements in some way function like this. When you take the temperature of something, this measurement is really something very, very complicated, if you think about it. It involves millions and millions of molecules, and it's a statistical average. So, but when you take the temperature, you only get a single number, Like if you take a thermometer, put it in someone's mouth, you get some reading of temperature, 30, 37, 38, whatever it is. And then, but that temperature is the result of a very complex process. That's actually a very complex function. So machine learning in this way also creates complex functions on domains and assembles them from the data itself, right? So all right, so that's just that's a more mathematical perspective on what machine learning does, right? So as I said, functions have a domain and a codomain. Domain is a set of data vectors. Now here I just showed the domain as an abstract set, but typically the domain would be something in a multi-dimensional space. Okay. So is often thought of as something in Rn. It's a multi-dimensional space. So you know, if I have 2 dimensions, I can write two directions like this. This would be R3. So I'd have 3 basis vectors like this. But of course, for practical data, you're going to have many, many more dimensions. E4, E5, E6. I can't draw this in 3 dimensions, but these would all be distinct dimensions. So typically, the domain is a multi-dimensional set. Now, each number in this array is called a feature. So in this case, if I have 1, 2, 3, 4, 5, 6, 7 dimensions, I would say there are 7 features that I am using in the function that I'm creating with machine learning. As I said, the codomain can be either continuous or discrete. Continuous is real valued or real vector valued, and discrete, the values represent classes or clusters. So I've covered this already. So these are all okay. Okay. So the function in effect performs a measurement on the domain. So I talked about thermometer. Now, one example of discrete function is counting votes. So of course, you know that the US election was just complete, and there's a great deal of controversy over vote counting. You would think this would be something very simple, but in fact, it's not so simple. As you can see, there are court disputes until now. It seems like things are clearing up now, but votes should be either yes or no. You mark the box or you don't mark the box. But some people may have marked the box too lightly. Some people may have missed the box. Some people may have ripped the paper. There are many other things that interfere with the counting of votes. So you can see that even in daily life, functions that are discrete functions are not so straightforward. And machine learning is a reflection of this truth that real life functions are very complex and involve multiple factors. Another example of discrete function is identifying letters. This is one of the early successes of machine learning. Some of you may know about Linnet, which was Yann LeCun, and he used a neural network to identify letters, and now the US Post Office uses this system to automatically identify addresses and people's names. Okay. Okay. All right. So as I said, I already said vectors lie in a multi-dimensional set. This is, for you mathematicians, this is not necessarily a mathematical vector space. You may not be able to add vectors. You just have a set, an array of numbers. Now, it's important to try to understand the shape that the vectors occupy. So I can explain that. If you know anything about statistics, and I will be talking quite a bit about statistics in this talk, because statistics is the root of machine learning. If you know anything about statistics, you know something about the shape of the data. You have a often you have a data cloud. So here I have an example of 2 dimensions. And maybe I have some data which is scattered here. Okay. Okay, so I have several data points that I've taken. Okay, and you can see that this data cloud has general shape of, it's kind of elliptical, and and the ellipse is tilted here. So I can take this ellipse and I can actually identify two axes, this axis and this axis, which define the shape of the ellipse. And these are called principal axes. Okay. Now here you can see that in this case, the axis here, the axis that's tilted to with the upward slope, has more variation than the axis in the other direction. So you want to identify, this helps you identify the directions of important variation. Okay, so where the data lies along this line is more important, has more of an effect of where the data lies along this line. Okay, so if I only know where the data lies along this line, I have more information than if I know where the data lies along this line. Okay, so this is related to what you may know about PCA, principal component analysis. Okay, so this is one example of finding the shape of the data. This is one way to find the shape of the data. Okay, and the importance of PCA is it can simplify the data representation, and it reduces the effective dimension. Okay, so it may be able to, it identifies the important dimensions, and you can eliminate the unimportant dimensions. So this data reduction is a very important part. It's a very important concept in any kind of data analysis, and machine learning in particular. Let's see. Okay. All right. So there's some question. All right. So so I hope the board is visible. If the board is not visible, all right. So let me hear from people. Someone was not able to see the board. Who could I say I see a yes from everyone who can see the board?
Yeah. Yes, we see the board.
You see the board? Okay.
Yeah.
That's fine. But right. Okay. All right. Good. All right. So. Okay. All right. So so let me go on. Data vectors can be discrete measurements, continuous functions, images. So images are the data vectors that we used, or some combination of all three. Okay. This gives somewhat an idea of the power of machine learning, is that it doesn't really matter what your data vector is. You can use similar techniques that apply. However, certainly if you apply these techniques to image data, you would use very different procedures than if you were applying this technique, say, to sound data. Right? Because you need to take into account the characteristics of the input data. And that's what I'm talking about when I talk about the shape of the vectors. Okay. Right. So I also mentioned this, that continuous functions usually can correspond to predictions. So in fact, in our work, we used a continuous function to characterize groundwater level. So groundwater just means the basically the amount of water that is it's kind of the level of water or water table present on the land. Now, the thing about groundwater is it's not quite the same as rainfall. If you talk about rainfall, if you have rainfall that you have 2 centimeters today, then if you have no rainfall tomorrow, then the rainfall goes from 2 to 0. Now, groundwater is not quite like that, because groundwater, you have slow processes like evaporation or rainfall that change the groundwater more continuously. If I have a rainfall 2 centimeters, and that raises the groundwater by a 2 centimeter level, then tomorrow I will still have a raised level. So it's more, so I can say that groundwater is I can say it has residual. Okay, so if I say the groundwater at time t depends strongly on the groundwater at time t minus 1. Okay. Okay. So it has this kind of residual property, but there's also has some periodicity. Okay. Because you would expect that if the year has dry seasons and wet seasons, then the groundwater level will follow the season. Because during the wet season, the groundwater will accumulate and become higher, and during the dry season, it will become lower. So it has periodicity, and the period is 1 year. Okay, so you really have 2 types of influence on groundwater. You have influence from the previous time. If I'm looking at groundwater on a monthly basis, then my groundwater level this month will depend on the groundwater last month. And also, the groundwater will depend on a yearly basis. As the season precipitation changes, the seasonal level will go basically up and down. Okay, so I can say these considerations tell me something about the shape of the data, and my machine learning algorithm should take this into account. Okay, all right. So so I mentioned that besides having continuous functions that can be used to predict, machine learning can also be used to classify. And I did mention also clustering. In clustering, you look at the data to decide what classes should be there and how many classes, or you can assign vectors to a predefined type. Say if you have a set of people and you want to assign an image to a particular set of people that you know. So this would be a classification problem. Okay, so in our research, we define a positive continuous function on sequences of time-ordered images where the function value is a pixel by pixel prediction of the next image in the sequence. So I'll show you what I mean by this. Just briefly, I'll say this here. Okay, so if I talk about image prediction, okay, so if I have a sequence of images, okay, so let me represent my sequence of images this way. Here's an image here, here's an image here, here's an image here, okay, okay. Now, in our case, the images are taken at a monthly interval. So say this might be March, this might be April, this might be May, June, and so on. Okay, and so on. Now you know that images are divided into pixels. So it's not quite continuous, but they're divided into pixels. Okay. Okay, and so on. Okay. Now, we are looking at the case where these, where these are known. So these are known images. And you want to use these to predict this image. All right, now how can I predict this image? Well, this image also consists of pixels. All right, each square here represents a pixel. So I want to predict this image. I could try to predict the entire image, or I could try to predict the image pixel by pixel. So I predict this one pixel based on this past data. I also predict this one pixel separately based on this past data, and so on. So I can do pixel by pixel prediction. Okay. Now the alternative would be whole image prediction. Okay. This is more like a classification problem where you, in the case of facial recognition, we could call that an entire image prediction. But we want values at each pixel because we're interested in the rainfall at different locations. All right. So I actually need a different function for each pixel. So we used machine learning to define a function for each pixel. Okay. All right. So you could think of this as multiple functions, or you could think of this as a single vector valued function. Okay. And that gives me my entire image. Okay. All right. As I said, please don't hesitate to type your questions in. If I don't see it right away, I will certainly get back to it eventually. All right. So let's go on. Okay. All right, so let's get into more of the details of how you actually define this function. Okay. As I said, a machine learning function is based on data. So you do need a reserved set of data that is used to define the function. And this is what we call the training data. Okay. Now this training data should be representative of a certain type of data. For example, if I want to make groundwater prediction, I should use data that's representative of groundwater over the long term. If I'm interested on groundwater from year to year, I should certainly include more than 1 year of data. Since the variation is very strong from year to year, I should try to include as many years of data as I can. But this data should also be in sequence. I need to have complete sequences if I want to use sequences of images to predict images. For instance, in this case here, I'm not just using a single image to predict this image, I'm using multiple images. Now, why am I using multiple images? Because as I said, groundwater depends not just on the previous image, but it also has some seasonal dependence. So the image at this time, the image in July, the value is, you could say, is influenced by previous Julys. And you get valuable information about this image if you know something about the images on previous Julys. So you want to use more than just one image to predict this new image. Okay. For those of you who are mathematical, that means that this is not a Markov process where the present depends only on the previous, but the present depends on several previous images. Okay. Okay. All right. So we want to create this function, we want to use some training data, and this data should be representative because I want to generalize the function and use the same function on other data. So the function should be generalizable and not, sorry, let me go back up, and not particular to the data used to create the function. Okay. So if I create a function that's very good only on the training data, it's not useful for me at all. Because what's useful is what's useful is a function that can be used to make new predictions. Okay. So there was a question here about the picture I made here. That so it says so this scatter plot here, and does this give the shape of the data? And I would say yes. Notice that even without this principal component analysis, just plotting the scattered data gives you some idea of how the data lies. This really shows the importance of visual representation. Now, applying this picture to our current situation is a little bit more complicated, because if I try to represent this in multidimensional space, this has a huge number of dimensions. Each pixel has a value. If I use grayscale or brightness to determine the value of each pixel has a value. There may be thousands of pixels in one image. So each image gives me thousands of dimensions instead of just two. Now I have multiple images, so that gives me tens of thousands. Okay, so we're looking at a data vector that has tens of thousands of components. So it's not very easy to imagine a cloud of points associated with this data. Nonetheless, the concept still holds that your data is a point in multidimensional space, and these points do form a shape, and there's some dimensions that are more important than others. For instance, there may be some pixels, say in a desert area, maybe down here, maybe the pixel down here in the lower left is a desert area, and there's very little rainfall down here, and the groundwater level is always close to zero. And this is possible. Okay. In this case, this pixel is not very important in the prediction. You can just say, I don't really need to know what the groundwater level is at this pixel, because I know that it hardly ever changes. Okay. So this is this example of a feature that's not important, and I would not want to include in my function. So the art of machine learning is identifying important features that you can put into your machine learning function. Okay. All right. Okay. So let's see, where am I? Whoops, let me go back again, not quite done. Okay. 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 So the method of creating the function must be carefully crafted so that the function is both accurate and generalizable. I want to make a point that machine learning is an example of artificial intelligence. Or maybe the other way around. I forget which one is contained in the other, but artificial intelligence is no substitute for human intelligence. It's not a substitute. And I think sometimes people forget this. They say, I want to let the machine learning do all the thinking for me. No, you need to intelligently tell your machine learning algorithm, you need to set it up for success. You need to arrange your algorithm so that the machine learning will be able to make an intelligent decision from the data. So as I said, that's why you need to understand the shape of your data, and you do need to understand statistics. Okay, so let's see. All right, so I said the method has to be carefully crafted. Okay, and this is what is called feature engineering, is a part of this. That's an important part of this. how do you choose the features that you actually put into your machine learning function. Another is architecture design. Okay, this is especially important when you do neural nets. All right, so I want to make sure that my function is both accurate and generalizable. So one way to do this is to verify the function, and the function must be independently verified apart from the training data. The training data is used to train or create the function. You need another set of data called the testing set that you use to verify the function. Okay. So you need both of these things in order to make a successful machine learning algorithm. All right. Okay. So as I said, in our research, we create a function to be applied to future data to predict future groundwater values. All right. So I mentioned there are 3 tiers of machine learning. The first tier I would call classical or pre-computer machine learning. So there was a certain kind of machine learning before computers. And the most important example of this was multivariate linear regression. So this is a classical technique from statistics. Okay. Now statistics overlaps quite a bit with machine learning. And I do encourage you to learn as much statistics as you can, because many of these statistical concepts will help you in your design of machine learning algorithms, and will also help you to avoid many of the mistakes that people make when they use machine learning. So multivariate linear regression, this is a very, very well-developed theory. And those of you who are statisticians will know that there are many aspects to statistics and many ways in which it can be used for different types of data. So for instance, linear regression can be used both for continuous and this would be for discrete. So linear regression can be used both to classify and to make predictions. Okay. There are also techniques to get to use in regression that will do the data reduction for you. Lasso does dimension reduction. That I've talked about before. Now, I want to emphasize that multivariate linear regression is a serious competitor to more modern methods. And I will make this point again, that you should not jump immediately to the modern method without making sure that it really is better than multivariate linear regression or similar methods. Because often multivariate linear regression is as good as you can do based on the available data. And there are actually statistical theories that will talk about this. You may, if you're in statistics, they talk about a blue estimator, which is the best linear unbiased estimator. Okay. And this word best means the best. In some cases, linear regression will give you the best possible, mathematically the best possible result that you can get on your data. And trying to use something more complicated will only reduce your accuracy. Okay. So this is very important. If you don't know about multivariate linear regression, I encourage you to investigate this. Okay. Another classical approach is k-nearest neighbor. And the idea of k-nearest neighbor is very simple. In order to make a prediction for this point, I just look at its nearest, I look at nearest neighbors and decide, if I know the behavior of the nearest neighbors, then I can estimate the behavior of this one. Right. So this is a very simple idea and very fast to execute, but the performance may not be as good as other methods. Again, k-nearest neighbor can be continuous or discrete. Another one is k-means, which is used for clustering. So we actually used multivariate linear regression as one of the methods in our research. Okay. All right, now the second tier of machine learning algorithms I would call modern. Okay. This is heavily computational. You can't do it without a computer. And typically it requires an exhaustive search through possible models. So that's why it's very, very heavily computational and you cannot do by hand. So examples include random forest, extreme gradient boosting, support vector regression, and multilayer perceptron. So these are very prominent examples. Now, multilayer perceptron, I can say, is on the borderline between a modern method and what I would call a deep learning method. Okay. So there aren't really clear boundaries between these things, but you can give a general idea of how these different algorithms relate to each other. Okay. So in our research, we actually focused on modern methods. We did not use deep learning. And I'll explain why in another slide. Okay. All right, the third tier of machine learning is deep learning. So this is, you can call this is really state of the art. But you can't always use deep learning. So deep learning is extremely heavily computational. And even 20 years ago, deep learning was not possible because the computers of that time were not powerful enough to implement the convolutional, or the very, very large neural networks, the very, very large structures that are needed to make machine learning work. So basically, deep learning is a multi-layer perceptron with many layers. And I can say plus specialized layers. I'm not going to talk about what I mean by a layer. I think that many people have some idea what I mean by this. But it basically means, I can just say that a layer means that you take your input data. So I'll call this layer 1, layer 2, layer 3, layer 4, layer 5. And here's your input. And here's your output. And your data passes through several stages. Your input data may go in several places to the first layer. Then the first layer connects to many places in the second layer. Each output of the first layer may connect to several inputs in the second layer, and you have this pattern continue like this. Okay. And of course, this continues all the way down. Now, the way these layers connect relates to what you would call architecture. You can have fully connected layers where every output of layer 1 connects to every input of layer 2. But that's I can say that's overdoing it. You want to arrange your layers so that the outputs go selectively to well-chosen inputs. And that's the idea behind convolutional neural networks. A convolutional neural network has layers that are not fully connected. Not every output goes to every input, but outputs from here go to carefully selected inputs in the next layer. Another variant is recurrent neural networks. So I won't talk about that. So characteristics of deep learning need lots of data. And I think that all too often people underestimate how much data you need. Okay. So I'll talk about this later. And there are many, many, many choices for the architecture and for optimizing. So this is not something to go in lightly. There's a lot of background that's needed before you can use deep learning. And the best way to use deep learning is to use a model that someone else has developed and to enhance it. And these choices, the optimal choices for architecture and optimization, they're not well understood. People just learn from experience. Why is this architecture better than the other one? People don't know. There's no theory that informs this decision. Okay. Now, I will say that we did not use deep learning because our data set really was not large enough. Even though each image has a lot of information, you also need a lot of images. And we only had a few hundred images. That's not enough to use deep learning. And I will say that one of the problems with using machine learning is finding adequate data. And in Africa, if you're looking for good data in Africa, I think it's very, very difficult to find data sets, African data sets that are applicable to deep learning. All right, I have a question here. Is GAN an example of deep learning? Okay, and I actually forget what this acronym is for. I think it means, I think it's generative adversarial networks. I think that's what it is. I think that's right. Someone can correct. Okay, yes, all right, yes, thank you. So Dr. Sawyer confirmed my guess. In this case, you have two neural networks working against each other. Okay, and in fact, yes, this is certainly an example of deep learning. So there are many exciting developments. Okay, so I'll read this from Dr. Sawyer gave you in the chat, he gave you some more information about generative adversarial networks. Okay, so there are many exciting developments there. Okay, all right, so let me talk about making the right choices. So in our particular research, of course, we had to make some choices, and I will walk you through some of the choices that we had to make, and maybe you can learn from the process that we had to go through in order to make this prediction work. All right. So as I said, I'm going to summarize some of these right choices by giving you 6 thou shalts. So these are 6 commandments of machine learning. And I won't say that they're comprehensive, but they are 6 things that you should keep in mind when applying machine learning. So here's a diagram of the algorithm flow that we used in our research. First, we start with the image data set, which was obtained from the internet. Then we select features. So this is feature engineering, and use this feature selection to perform pre-processing on the data set. Okay. As a result of pre-processing, we create a training set and a testing set. As I said, the training set is used to create the function, and the testing set is used to verify the function. Okay. So with a training set, you train your machine learning function. You create trained models. Now, when I say model, a model is basically a function. And you use this trained model to evaluate on the testing set. And we had several trained models: support vector regression, random forest, linear regression, multi-layer perceptron, and extreme gradient boosting. Okay. And the 6 commandments that I'm going to introduce relate to different parts of this process. So I'd say the image data set relates to commandment 1, then commandments 2 and 3 relate to pre-processing, 3 also relates to training and testing, and 4 and 5 relate to the methods, and 6 relates to the evaluation. Okay, so again, I'll go through this block by block as I explain what we did. Okay, so here are my 6 thou shalts. Number 1, understand thy data. Okay, number 2, pre-process thy data intelligently. Number 3, maintain data integrity. Number 4, compare with a simple baseline. Number 5, use an algorithm appropriate for the amount of data. And number 6, determine the significance of the results. Okay, so these different commandments relate to different parts of the machine learning process. Okay, so you can take these commandments and put on your mirror, and you can memorize these commandments. All right, so I hope I can show you how these work in practice. So I said, understand thy data. That relates to the image data set. So you need to know what you're dealing with. So your image, you actually have to change this data set into a data vector. And changing your image into a data vector depends on your understanding of how the data works and how the data relates to what you're trying to do with it. Okay, so all right, pre-processing. This is really a very key part of the process. This is where human intelligence comes in. This is really where human intelligence comes in. This idea of feature engineering. Okay, you also want to make sure that you keep the integrity of your data. That when you are processing your data, you don't lose essential information that will distort your results. Okay. Data integrity also comes into this stage here where you have training and testing. You want to make sure that there's no interaction between this. If you want to test the function created on your training set, you need to make sure that this data is quite separate from this data. So you want to have this data be independent. All right, the independent is a concept from statistics. If you have two variables that are independent, it means that knowing one gives no information about the other. So you want two sets here that really are independent so that you're not unfairly using information from the training set to get you unfair information about the testing set. So it is a truly objective test. Okay, all right, then compare with simple baseline and use appropriate algorithms. That goes into the choice of algorithms here. In this case, linear regression was a very simple and direct method to create a machine learning function. And we compare these other modern methods with this classical method. So don't leave this out. You do want to have some simple method to make sure that your improvement is truly an improvement. And then finally, the evaluation, of course, is a very important part. And you actually want to have multiple evaluations. All right. Okay. All right. So let's start with the commandment number 1. Thou shalt understand the data, which components are important and which can be ignored. How are the components of the data vector related to each other? In evaluating this, there's an important idea is correlation. Again, a statistical concept. Okay. Correlation means that two components give partial information about each other. Okay. For example, suppose I have an image and I have pixels. Okay. And I take the pixel here and the pixel next to it. Okay. Suppose the groundwater level here is low. Suppose the groundwater level here is 0. If the groundwater level here is 0, I would not expect right next to it a groundwater level that is very large. In our case, the groundwater level goes from 0 to 255. So I would not expect the pixel level here to be 255. I'd expect the level here to be low. Okay. So this pixel has some correlation with the pixel next to it. Okay. This is not independent information. So, so that's an important thing to consider when you are arranging your input data vector. Now, sometimes you may have long-range correlations. It may be that the data has a large area of high groundwater. Okay, then you'd have some large, long-range correlations, and that's also important in considering how to process the data. Okay, all right. So here, here's an example of the data that we used. So this was data obtained from the internet, and what the colors here mean are groundwater levels. I think you can recognize the map of the world. Here's United States, here's South America, here's Africa down here, Australia. And you notice that there's only data over the land areas because you don't have groundwater in the ocean. So there's some pixels here that have no data. Okay. And of course, when you're doing your data pre-processing, you want to eliminate pixels that contain no meaningful data. Okay. All right. So this is one particular image, and we used monthly images. So each month had an image like this, and of course the only meaning of the colors is intensity. The reason why this images has colors is because human eyes prefer to see different colors. It makes the different levels more clear. But for your machine learning, the colors are not important, and in fact we want to change these color values into intensity values. Right? That will simplify the input data. It reduces the dimensionality. Okay, so this red would be a very large value, maybe 255. The dark blue is a very small value, maybe 2 or 3, something like that. Okay, so we're going to change all of these pixels into a linear scale. Now you can imagine there are many, many pixels. You can almost see a pixel is a square, very small square. This is a great deal of data. In order to try out our methodology, we looked at a much smaller area. And you can imagine that the groundwater in Southern Africa has very little to do with the groundwater up in Greenland. So it does make sense to look at an area, to focus on an area in the analysis. Okay, so we looked at global satellite data, monthly images for 174 months. So the color scale maps to groundwater level, and then this is all right. So this data was too large, and these geographically separated regions are not correlated. So there's really no need to look at the entire image at once. So we selected a smaller region for our purposes, and we want to use a sequence of monthly images to predict the next month's groundwater level on a per pixel basis. Okay, so I got a question here. Why is validation set not under the maintenance of data integrity? And there's a question about about the validation set. Certainly the data validation set, also you need to be concerned about the integrity. You do need to be concerned about that. Okay. All right. So step number 2, pre-process thy data intelligently. Okay. As I said, you want to remove the background pixels that have no information. Okay. All right. So you also may need to do data imputation if there are images missing. If I need a sequence of images to predict an image and there's one missing, then what do I do? How do I fill in this missing data? Data imputation is a very common problem in statistics. So there are many techniques for this. in our research, in this particular case, one way to impute data is simply repeat the previous image. So simply take this image and use the same image here. This is not the best method, not the most accurate, you can get better results with better data imputation. But this is also an area of important area where there's a lot of research going on. But you do need to find some technique for filling in missing data. Okay, all right. Now, if your data is periodic, then you can remove periodicity by averaging. So I mentioned in our case, the data had a yearly period. We did not actually remove the periodicity, but we accommodated the periodicity by another method. Okay, so you can remove the periodicity by averaging. Okay, and subtracting the periodic average. Okay. Another thing that you want to do is maintain adjacency in two-dimensional data. Okay. If I have two-dimensional data, as I mentioned, this pixel here has a close relation with pixels that are close by. And in your input data, you want to make sure that you don't separate these pixels so that they don't influence each other. There's a temptation to take this image here and stretch it out into a linear vector. So let me show you here. Okay. Okay, so I can say adjacency. Okay, so if I have image data here, and let's say the pixels go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now this pixel 8 is next to pixel 3, pixel 7, pixel 9, and pixel 13. Okay. These pixels next to pixel 8 contain information that can influence pixel 8. But if I stretch this out into a vector, I would just get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. In this case, you can see that the pixel here, my pixel 8 is here. And the neighboring pixels, 3 is a neighboring pixel, but it's been moved away. The 7 and 9 are close by, this good, but this 13 has been moved away. Okay, so you've lost the adjacency information. You want to make sure that when you convert your original information into a data vector, that the close by data stays close by. Otherwise, you may not be able to make such a good prediction. All right. So one of the ways to improve the performance of your predicting function is to use something called data augmentation. So I'll say a little bit about that. So data augmentation means that you use available data to create additional, I can say artificial data that is nonetheless representative. Okay. So let me give you an example. Okay. Suppose you're trying to make a machine learning for identifying, let's say that you want to identify leaves. Okay. Now you know that a leaf looks something like this. A leaf looks something like this. Okay. And maybe you have some images of leaves like this. Okay. Okay. Maybe another one may look something like this. Okay. And so on. Okay. Okay. And you want to use these images to train your machine learning to recognize leaves. So maybe you only have a few images. Okay. Now you can take these images and modify them. Okay. Now if you have a leaf image, you can modify it by rotation or scaling. Or you might change the brightness. Okay. There are various things that you can modify, and the image still can be recognized as a leaf. Okay. For example, I could take this image here and I could rotate it. If I rotate it, it might be something like this. But it's still a leaf, and I can still recognize as a leaf. So I can add these modified images to my training set. Okay. All right. Now, so you have to be careful to preserve what I would call data integrity. For instance, in our case, let me go back here. In our case, let me show you. We're looking at this particular image here. Right. Now I could certainly take this image. Is it going to let me copy? Okay. Oops. Okay. I could take this image and I could rotate it, or I could invert it. It's not going to let me invert. I wonder if I can rotate this. All right. It's not going to let me rotate. Maybe, well, let's see if I can do this. Oh, here we go. I can rotate. Okay. I could rotate this way. Right. And I could say, okay, this is another image I could use as a data vector. But notice what you've done is you've destroyed the geographical information, the important geographical information. So by rotating, you've destroyed the data integrity. So so I can say the geographical info. Okay. It's important that this pixel is always in the same place. But now you've moved it. Now it's over here. So if you rotate this image and add this to your data set, you are creating false data. It's not going to improve the performance of your algorithm. So you do need to be very careful about that. Okay, let's see. Okay, so then there's a question here. Is there a limit to the number of modified images we can add? I don't know if there's a particular answer to that question. I think that has to be investigated empirically. So I guess that what I should say is I don't know, but I'm suspicious that if you add too many you do have to have enough genuine data to make sure that your algorithm is based on the actual situation. So I guess for that's a good question, but I don't really know how much you can do. I think possibly what's more important than the number of images that you add is how you add them and what transformations you use. All right, so let me go back down. All right, okay, another thing is if your data is time ordered, you don't want to shuffle the data. If I'm using a sequence of images, okay, if I'm using a sequence of images to predict another image, so I have image, 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 and these are time ordered, 1, 2, these are after each other. Now I could create another sequence by shuffling these. I can move 4 to here, I can move 2 to here, I can move 1 to there, and move 3 to there. So this would be 4, 2, 1, 3, and I could see if that predicts 5. Now the problem is that this order is important. This is a new sequence. Whoops, sorry. This is a new sequence, but you've destroyed the integrity of the data. You've destroyed the time ordering. Okay, so this actually gives you false information. You would never actually see a sequence of images like this where January follows March, but you're presenting this as typical data. Okay, so in this case, it's easy to see that you've destroyed the integrity. In some cases, it may be more difficult. Okay, all right. So there was a question again, why the rotated image was false. Again, I think all I can say is that when I'm predicting pixels, I have to use for instance, if I have a sequence of images, like this, okay, and I can take it, and I want to predict the next, so let's see. Let's copy this. Maybe this is more clear. Okay. Oops, sorry. Zoom out. Come on. Okay. Okay. Let's do one more. Okay. Let me see if I can, I'll rotate a couple of these. Okay. And maybe I'll rotate this one. Yeah, I think, all right, let me do this one. Okay. Okay, sorry, let me do it again. All right, so let me just do it with 3. Okay. All right, suppose I take rotated images and I rotate my images like this. And then I predict my next image. I want to predict the next image in the sequence. What's the next image I'm going to predict? Okay. If I want to predict it's looking at this pixel here. If it looks at the same pixel, in the different images, it's not really the same pixel. How is it going to predict the pixel, which is now the pixel is the original pixel is now somewhere else? Okay. The original pixel is over here, it's not over here. How is it going to predict the pixel over here, where the pixel in this image is over there? You've moved the pixel around. You want to keep the pixel in the same place because you want to predict the same pixel in the same place. If I was going to predict the next image in this sequence, I would probably predict that the image is rotated again. You don't want to predict the rotation, you want to predict the value of the pixel at that point. So that's why you have to be careful about not changing your image in a way that's going to change the information. All right. So here we talk about the pre-processing of the data. As I said, we convert the image to grayscale because the only thing that's important is the intensity. And then we identify possible features. So the most important features that are going to determine a pixel here in the new image are the same location pixels in the previous images. Okay. So here we have 12 successive images, and we look at the pixel in the same location, and these are potential features to predict the pixel at this location. And it looks like I'm taking much longer on this presentation than I thought, but I think it's good to talk about these things. Okay. All right. So the question is, these are potential features. Should I use all of these or not? That's a lot of data to look at to predict one value. Okay. So you can actually evaluate the importance of a feature using just the training set. Okay. This does not violate data integrity. This just tells you within the training set which features you expect to have a bigger influence on your on the image that you want to predict. This is one example of knowing your data. This is a way of exploring some properties of your data and then using those properties to find a better way to design your features. Okay, this is what you call, this is how you do feature engineering. Okay, so there is a way of using extreme gradient boosting or random forest to rank the importance of features. So I won't go into the details of that, but the result is here. F0 means, I'll go back here and show you. F0 means the same pixel 12 months previous. F1 is the same pixel 11 months previous. F11 is the same pixel previous month. So if I want to predict the pixel for a certain month, the same pixel 12 months previous gives me the most information. Next most is the same pixel previous month. This agrees with what I talked about earlier, that groundwater has both periodic and residual characteristics. The groundwater in the previous month, some of that groundwater is left over and will influence the groundwater this month. I also have seasonal variations. So the F0 gives you seasonal, and F11 gives you residual. Now, besides this, there is some influence of other months. This is the month before previous. This is the month after. I'm sorry. This is the month after 12 months previous. This is the month before previous, and so on. And you can see that these are much less important. So based on these results, this gives me some idea of the feature sets I should use for prediction. Here in this case, we used the same pixel 12 months previous and the previous month. Then here we use 12 months previous month, 11 months previous, and so on. So we are selecting pixels from which previous months that you will look at. Okay. Now, besides this, we want to have information that tells about the geographical and time-ordered structure of the data. So besides giving the pixel levels for different previous images, we also want to identify the XY coordinate of the pixel and the timestamp. Okay, so if I go back here, if I was going to predict a sequence of images here, let's just copy this a couple of times. Okay. Oh, it's not behaving for me. Okay, that's fine. Let me just do one more. Okay. So if I want to predict this pixel here, this pixel right here, okay. According to my specification, in the first feature set, if I take F0 and F11, I give the following information. I give the same pixel previous month, and I also give the same pixel, let's see. Let me just do it this way. Oh, there's another one back there. Okay, sorry. Just get rid of that. Okay. So I'll put ... here. Okay. So this is F13. This is going to be F11. I'm sorry, this is F12. This is going to be F11, F10, and down to F0. So to predict this pixel here, I would give it the pixel level here, the intensity here, and I would also give the XY location of this pixel, as well as the timestamp. So this might be January, February, March. This, I guess this would be something like a November, December, January. I also tell me which month it is, because that gives me my seasonal information. So the information I'm using for prediction is the X coordinate, the Y coordinate, the month, and the pixel values for 2 previous images. So that's going to be my input data vector for predicting this pixel. And as I said, I'm doing pixel by pixel prediction. Okay. All right, so let's go back here. Okay. All right, feature creation. Okay. Based on the nature of the data, we also created a non-local features. Okay. You would like to think that you don't just want to look at exactly the same location in previous months. You would also think that the surrounding neighborhood of the image may affect the groundwater level at a point. So we tried to use this idea to create some non-local feature where the value of the feature does not just depend on the same pixel. Not just the same pixel. Okay. Right. All right. So we fitted a single cluster Gaussian mixture model. So I'm not going to talk in detail what this means, but basically we find the regions of high intensity. So you can see high intensity here. These points here indicate that there's high intensity here. And then you try to fit a single cluster to this. Can I remove the, okay. You try to fit a Gaussian cluster to this image. So if I was going to fit a Gaussian cluster, the Gaussian cluster would look something like this. We take the center and the two principal axes, and we use these as features. This would be mu, this would be my mu x, mu y. And then this would be lambda 1, and then this would be lambda 2. Okay, so these are added as features to my input data vector. Okay. Okay. All right, so I mentioned this. I think I should speed up a little bit. I have another presentation next week, so I'll probably go more into detail, and we'll do more hands-on next week. So you do want to avoid the data leakage between training and testing. If time sequence data is used, the training and testing data should be time separated. Okay. Okay. All right. So I talked about this before. Compared with a simple baseline model, you do want to use something that is very basic and make sure that you have genuine improvements. Okay. And I talked about this also before. I think I'm going to skip over this and cover this again next time, because I want to leave some time for question. To determine significance of results. So let me just give an overview of what I'll talk about next time. And I think that I should give a little time for discussion. Okay. So you have to evaluate whether your machine learning algorithm worked or not. Okay. So we do have some results. We showed difference between different methods. Here you can see you have XGB, linear regression, random forest, multi-layer perceptron, support vector regression, and then this is just the mean. Okay, and you can see that in this case it looks like support vector regression is better than the others. Now, is this difference significant? Well, it's not easy to tell. It looks better, but does that mean it will be that it's truly better? And then if you applied this method in another case, it would still be better. That's not 100% established. It's plausible, but it's not been proven mathematically. Here you can see the different feature sets. A was the simplest feature set, and becoming more and more complicated. You can see that adding more complicated features does not improve your performance. And in fact, the simplest feature set has the lowest error. So these are error scales. And I'm going too quickly over this, and we'll cover this again next time. But here's one way to compare your data. You can see visually that your predictions seem to be accurate. You can also represent the residuals, which is the difference between your predicted and your measured. If the prediction is perfect, then all the data should lie directly along this line. So the closer your data is to this line means the better your prediction. In this case, the red and the green are two different predictors. The red is a better predictor than the green. Okay. And here, red and yellow. Yellow is a different predictor. If you compare red with yellow, it's hard to see which one is better. But this, you do need to find ways to represent the performance of your algorithm. Here's another way to represent the performance of your algorithm. This is called a regression error characteristic. And if you're a mathematician, you can recognize this as a cumulative distribution function. The higher, the better. So the red predictor is better than the yellow and is better than the green. Okay. All right. So I do want to leave 10 minutes for general discussion and questions. I know it may be a little difficult to discuss. Well, you can raise your hand for questions or discussion. And again, I will go back over some of this material next week on the 28th. So let me just, that's a lot of material. Let me just pause here and say, did you want to ask any questions or have any discussion?
Thank you so much, Professor Chris Tron. It's been an engaging time, and it's been a good delivery of machine learning techniques. Do we have questions? Please raise your hand using the Zoom tool, or you type in the chat box, the chat section, so that we could read, and then the presenter will be able to give us answers to these questions. That's Professor Tron.
Well,
Do we have questions?
I think not just me. We have several experts here that
okay.
Make contributions.
No problem.
I think many people are interested in neural networks. So I hope you're not disappointed that I did not talk about neural networks. But if you want to talk about those now, we can certainly talk about them now.
Any question?
I wonder if some people are working now on a machine learning model. If you are working on a machine learning, if you're working on a machine learning model now, please type in the chat window what model you're using and what technique you're using. And maybe I can address some of these things next week on the 28th. I can maybe be able to talk about that.
Sorry, okay. Professor Tron, for your attention. Next week, it's not next week, it's Saturday.
Okay. Oh, Saturday. Okay, yes. Okay, Saturday, the 28th. Yes.
Yeah.
Okay. All right, yes.
I could see some questions in the chat already.
Yes, it says, why do we use modified image? Is it due to lack of data? And the answer is yes. In the example of a leaf I gave, you know that not all of the leaves that you will be wanting to use your algorithm on are oriented in the same way. So in a way, you are intelligently predicting the type of data that you want your algorithm to be able to recognize. If I know that I'm going to have leaf data, let me, because I don't draw very well, let me say that I want to recognize faces. Okay, this is one example. Suppose I know that I want to recognize faces. Okay. Now in this particular image, the face is down here, but I may want to recognize a face that's up here. Okay. Okay. So I can add this image to my data set. Now it may also be that I want to be able to recognize faces that are this way. So I can rotate my face, and this is another typical image that I could possibly encounter to recognize. Okay? So in some way, you're using your human intelligence to know what type of image you want to recognize. So another question, is neural network a part of machine learning? And the answer is yes. Neural network is what I call neural network includes both the deep learning and multi-layer perceptron. Multi-layer perceptron can be thought of as the simplest example of a neural network. So yes, neural network is an important part of machine learning.
More questions?
Okay. 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 So difference between multidimensional set and mathematical vector set. Okay. So the difference between, if you use Python, so what's the difference between a multidimensional set and a vector set? Okay. So for instance, if I have a multidimensional set, if I have apple, banana, a pear. Okay. And then I mean, let's see. So I could code this. Maybe Apple codes as a 5. So let's, if I say apple equals 1, banana equals 2, pear equals 3. Okay. Then I would code the apple, banana, and pear as 1, 2, 3. Okay. All right. So I can call this is an array of numbers. I call this a data vector. But if I have another vector, suppose I had another vector, 3, 1, 2. Okay. I can't add these. If I add 1, 2, 3 plus 3, 2, 3, 1, 2, this just gives me 4, 3, 5. What does this mean? You can't add an apple to a banana. Okay. All right. So you can't add. Okay. So this is not a mathematical vector. Mathematical vectors can add. Okay. So typically in machine learning applications, you would not think about adding vectors. The vectors all stand on their own. Okay. Okay. All right. Some good questions here. Let's see. Okay. So Peter Yuba says, I'm working on classification of maze images using AlexNet. Okay. Very good. So I think you're probably using a lot of data augmentation, and you're using transfer learning, which I didn't talk about. Okay. Okay. And thanks, does use of modified image and real image give the same performance? And I think probably the answer is no. There are many examples of that you can read in papers how the using modified images together with real images gives better performance. Next, what is the relevance of machine learning to genetic algorithms? I think there is some relation. Genetic algorithm is used for optimization, and I think maybe the best answer for this is that machine learning does involve some optimization, because you're trying to find the best predictor or the best fit, and genetic algorithm is a way to optimize. So genetic algorithm could be used as part of the machine learning process. So you can't say machine learning is a substitute for genetic algorithm or vice versa, but genetic algorithms can play a part in developing good machine learning algorithms. Okay. Next one, is pattern recognition a model of machine learning? Yes, pattern recognition is a kind of classification, right? If you are trying to put a label on different patterns. So yes, you would call pattern recognition a kind of machine learning. Okay. Okay. Is it purely a development of fuzzy set? Now, you can always bring fuzzy sets into this. Instead of making a hard classification of different objects, you can assign a fuzzy membership function. I really don't know too much about this, but this is certainly conceivable. When I did this, showed this function up here. And when I showed this function, which, where did it go? Here. and I divided my domain into distinct classes. Now, instead of dividing into distinct classes, you could create fuzzy membership functions. So you can certainly apply deep learning together with fuzzy sets together. Okay, so I would not say there's similar or difference. I would say that using fuzzy sets is an enhancement of this basic machine learning approach. Next question. What happens to the predicted image if one or more of the sequential images got missing? Well, if you think about in our case, if I want to predict July and the previous February is missing, the previous February is missing, I want to have the best idea possible of what that missing data was. So I try to use the best method possible to guess what that missing data was. Now, in our case, when we did feature selection, when we selected our best predictor was just using the previous month and 12 months previous. So in that case, the missing data is not as important. All right, so then next question. So I have 1 minute to finish up. What is the feasibility of machine learning techniques? That's a very general question. I think that this also is determined by experience. There are some times when machine learning techniques are not used in appropriate ways, but there are ways to evaluate the performance. So how do you test for significance using machine learning approach different from existing statistical methods? So let me talk about that next time. Basically, you do use an error metric, and the significance in machine learning is not as rigorous as significance in statistics.
Yeah.
There is not a systematic theory of significance like there is in statistics. Okay, last question. In terms of the mathematics of neural network, apart from backpropagation, what are the methods available in literatures? So backpropagation is a way to train your neural network. I think that is the most important one. I'm not really aware of other methods of training. So I can look into that, or we can talk more about that next time. But I think my time is up. I don't want to go past my allotted time.